Okay, thank you. I'm a bit impressed to be here after 5 years, but I'm glad we're having this session. There is a lot of great news and ideas to discuss on sulfates. So yeah, happy to be here. So we know sulfates have been mapped globally for Morbid. These are a few examples of, see the pointer, of reference stratigraphies that show sulfate-bearing lithologies according to orbital data. But the issue for Morbid is that we can't really resolve lithologic information crucial to understand. The major question remains, what's the environments recorded in this strata, and what's the origin of the sulfates? So for this, we need to land. And thankfully, that's what we've been doing. So we have good data now accumulating. And in particular, at GEAR, with Curiosity, we're recording a large reference strata with sulfates. And we can now try to unravel what is the meaning of that transition, that global transition of environment from the Noachian into the Hesperian that Mars has recorded here. And so in the past 5 years, we've been going right through ascending the sulfate-bearing units. It's a massive 800-meter thick unit. We are almost half through it. And, but that's not the first time we've already seen sulfates in the past, like with Opportunity. And here we've seen sulfates, although only 7-meter strata. This is part of a much wider unit that is bigger, but we've seen only 7-meter in situ. And here we've seen loads of sulfates, enrichment everywhere in the bedrock. But we've seen a mixture, including iron sulfates and jarosite, that is diagnostic of extremely acidic environments within a dry aeolian sandstone. So late groundwater going through and precipitating jarosite is extremely acidic. So that's what we learned at that location. And guess what we've seen at GEAR? Well, nothing really exactly like this. Instead of sulfates being everywhere, they are patchy. We see mostly like smooth bedrock here, like you can see as an example. It contrasts sharply with nodular bedrock. Here you see sulfate versus calcium-magnesium cations, showing that the sulfate enrichment is associated to nodular bedrock to a lesser extent compared to the bulk that's been found at Burns. And the smooth is somewhat enriched, but much less. And here you see the variability of this nodular bedrock, and it's mostly magnesium sulfates, not iron sulfates, and no sign at all of jarosite there. So the same data showing in elevation. Here you can see a stratigraphic column showing really well that we have seen that transition into the sulfate-bearing. It's pretty sharp. This sulfate content measured on every point by ChemCam, and the average shows up very well. Before, we haven't seen so much enrichment, and since we're there, the nodules are carrying most of that sulfates that we see for Morbid in that reference stratigraphy. So the environment and the record, we've seen there large-scale crossbeds that are obvious here in region. Here's an example. But if you look closely, you see also smaller features like these lenses and those that have finer scale sedimentary structure. And upon close inspection, we've seen this wavy pattern that corresponds to a symmetric wave ripple recording a wet surface environment, a pond. This in the lens is an interdune wet deposit, an interdune pond in between aeolian dunes. And at the top here is even a regional surface that has those wave pattern characteristic of a shallow lake. And what we can do at GEAR with those large structure, this combination of large and fine, we can have something that is not a luxury to appreciate large sedimentary structure, are large buttes. Here you see 100-meter thickness buttes exposing that sulfate-bearing strata. And we can use that to understand the general architecture of that. Is it always the same? How is it changing with elevation at a 100-meter scale? And we have, so close image here, you see, for instance, 2 intervals of different sedimentary structure. You see clearly at the top planar features that are cross-cut at this erosional contact, and in the part below, large-scale crossbeds with lenses. And on closer inspection of the lenses, you see small-scale sedimentary feature, including wavy pattern that is evidence of those wet interdune sires. So they seem to occur, and there is a specific architecture to it going into planar upsection. So having a global look looks like this. You don't need to look at all the details, of course, but this is all the strata that the rover has been through, driving, putting the wheels on, and these are strata has seen on larger buttes that we have the cameras to do the inspection. So you see the sedimentary strata, and we can look at the lateral consistency of those sedimentary structure and turn this into a model of expected, what were the dunes doing, were they eroding, were they depositing relatively a lot less, and where was the water table at the time? And at a large scale, this is what we see. We turn from a damp environment into this, what looks like a regional unconformity that's been mapped at the scale of Gale, into a dry environment, and then into a wet Aeolian environment, so still lots of sand, but also high water table. That is lowers into planar strata that is sand sheet into a regional deflation and back into lacustrine wet deposition. And this is actually known to terrestrial wet-dry sequences that have supersurfaces that are either bypass or deflation, depending on the timing and the intensity of the sand flux. At a large scale, it produces those type of packages. And it seems this is the type of things we see here at Gale, the relative timing of the high sand flux or the high water table or the lower water table that are given on Earth. We know this is climate or regional forcings on the hydrology and the source of Aeolian material. And another thing you see, so in that context, what is the timing of nodules? This is crucial. And so to understand, is it early or is it late relative to all that strata being deposited? If it's late, the nodules we've seen are intra-sediment salts. They need to form in the porosity. So what's the highest porosity? The most likely porous is a dry Aeolian sand, according to that scenario of deposition. But when you look at the density of nodules stratigraphically, it's actually the location we found the least of the nodule. You can see the density being tracked as a function of elevation. Here, low or less than 5% of nodules are seen consistently here in that strata, which would be the most porous. So something to consider about the timing that is hard to resolve, but still magnesium sulfate is an extremely soluble salt. It's the dominant salt we find in the sulfate unit. It requires evaporation to precipitate. And also nodules are cross-cut by veins, predates fracture and exhumation. You have a talk by Sina after me to go into detail into the nodules and their distribution. Here, I'd like to insist that nodules appear associated with what used to be high water table at the time of deposition, instead of where the sediment porosity is the highest. This supports sulfates tracking as an early evaporitic origin. Another outstanding feature we've seen with the sulfate is this. At the base of the section, we've seen nodules organized into polygons of 4 centimeter diameter in a pattern like this. We confirm the sulfate enrichment on the nodule, and we find this is not a surface pattern. It's actually a penetrative structure going into the rock according to that step lithology you can see here. It's also not unique. We've seen it across stratigraphic thickness at the base, about 20 meters of thickness. We've seen a lesser obvious version of those polygonally organized nodules. And what we think here is that this fits a model of formation has a columnar soil as an Earth analog. You see here, if you cycle a soil that aggrades vertically into drying and wetting, the cracks will form characteristic Y-junction, and the salt that crystallized in the fracture here gets preserved. It's protected from flooding. If you repeat that intensively, as the soil degrades, you need to be in an aggraded regime instead of an erosional regime, then you bury columns. And then those litify and exhume in an hyper-arid climate that marks today into ridges. So what used to be fissures become ridges. This is characteristic of regular, cyclic, and seasonal hydroclimate on early Mars. How do we have? Someone needs help. I think someone needs help, so.
Take a little break for a couple
Yeah.
I'm calling security right now.
big round building. All right, thank you.
Is it briefing?
It's inside, yes. We've got a conference going right now. Dwayne Miles, the stage manager. All right, thank you. All right, security's coming over there.
Okay.
They're all EMTs.
Oh, well,
So,
that's
yeah.
good. Yeah, I think we should wait and.
Yeah.
Yes.
Okay.
I don't think you want to kind of continue.
Yeah,
to right now.
of course. We suggest to wait
Yeah.
for a minute for.
They're over there. No, he's sitting in the seat right now. Somebody's away.
Right.
Yeah,
Yeah.
we have time to talk about sulfates. It's okay.
He's sitting with him. He's just sitting in the seat right now.
Okay, he's breathing. Was that good on time already?
I think there's a little over 2 minutes left.
Okay, good. Then I can take my time.
Okay. I mean,
Sorry, I didn't see I was too focused.
yeah. Oh, you didn't see the 5? Oh, okay.
That's why I'm bad.
Oh, I know. Well, at LPSC the last 2 times, the speakers here, and they've had the numbers like way down on the thing, so you can't see them. You have to step to the side of the podium to see the times. And it's just like, what are they thinking, you know?
Yeah.
So, the guy, did you notice that somebody had a seizure or something? Yeah, you saw that.
Yeah, I said that something.
Yeah.
So.
Yeah.
Sorry about this session.
Yeah. I don't know. Somebody's health is more important.
Yep. I see him breathing, so it's reassuring.
Yeah. Just in case there's like a heart issue or something, I think they should take him to the hospital to make sure.
Yeah.
I mean, if it's just a seizure, I guess that's different, but I don't know if they can give them medicine for that. I don't know, but if it's somehow a heart,
I wish I would be training for that.
yeah.
Have you done training for that? I know there are.
A CPR, you know, at the SETI Institute a long time ago, they offered a training, and I had, like, I paid for all my students. It's like, I want everyone to learn this, but you have to get refreshed every 2 years or something, and that was, I don't know, like 15 years ago, so. Yeah, I think it's a good thing.
Yeah.
Oh, yeah, of course. maybe we could, you transitioned, back a slide, because it was a big transition to the, this part. Maybe go back one. Let's see if we can, okay,
I got that, this one.
yeah,
All right.
okay. Well, it's like if you're watching a movie and there's an interruption and you go like back to the little 15-second thing.
Yeah.
So I didn't realize they were videoing it, but I guess they are. Because I know it's an in-person conference, it's not a hybrid.
Right, so, okay. Well, I cannot reproduce the same thing, but
Oh, it doesn't matter, yeah. Well,
I'm going to check on Jeff because
yeah. So everyone, let's take a seat again, and it looks like our medical emergency is getting resolved, and we'll I've asked William to sort of go back a little bit and start the last sort of section he was talking about, because we were sort of mid-sentence there. And should we wait for them to close the doors maybe? Or do you, yeah. Okay, I think we're ready. Let's go ahead and pick up where we left off.
all right, thank you.
Maybe like 2.5.
I hope Jeff's going to recover well. Thank you. So we were talking about this unique lithology that we've seen at the base of the sulfate bearing unit when we entered. And here we found the sulfates enriched in the nodules, but the nodules are organized into coalescent ridges forming a polygonal pattern. And the important thing is that this polygonal pattern is not just a surface pattern, it's a penetrative structure that's in 3D inside the rock, in the structure of the rock. And so we haven't seen, so it's not unique. We've seen it in a stratigraphic thickness across the base of the section of the sulfate bearing unit. What fits this lithology is the columnar soil that is known as a terrestrial analog. We see some on Earth that have the same properties. This form using sustained wet-dry cycling at a high frequency. These require the desiccation with a recharge occurring possibly seasonally or intra-seasonally at a fast rate. And as the sediment aggrades, you produce those columns with sulfate enrichment that is protected and preserved in the sediment. And as it's lithified and exhumed, they are exposed here on Mars as ridges because of the preferential cementation with sulfates that makes the ridges, the sulfates, a positive relief. What's important is that this is sign of a regular cyclic, possibly seasonal, hydroclimate regime on early Mars. Really, you cannot make this rock if the hydrology is driven by volcanoes or impact. So you need a regular return of surface water. You need it to be regular. And why is that important is that we have now wet-dry cycling occurring at various scales. And wet-dry cycles are important because in our search on the origin of life, we know that we had all the ingredients on Mars, but for organic matter that's being delivered, here you see the chronology of being delivered on the surface into a hydrologic system. For this to self-organize, we know only a few processes. And the past decade in the lab have shown that wet-dry cycles at a high frequency can spontaneously form polymers from monomers, and even biopolymer that are used then, we know, in life forms that we know on Earth, like peptides or nucleotides. And they can accumulate in this type of environment. So we know GEA is a reference strata for this type of clay sulfate transition, and we can go there to look for a record. There are erosive surfaces, but mostly this is a grading. This is preserving the history of that in an environment that's conducive to the prebiotic evolution. So take a message that sulfates and salts are your friends. They are no longer highly acidic, uniquely highly acidic. They can be associated with evaporating wet-dry cycling at various scale. You see like large sequences and small scale paleosols. We've also identified iron carbonate siderites in drill sample. This seems to be associated to it, so it's excluding highly oxidizing also environment. So all this to say that clay sulfate sequences may uniquely present a key record of pre-biosignature that we can look for in the future. There are plenty of those on Mars. And in the near future, there's more to come. We're continuing our ascent on Mars. There is hundreds of meters of sulfate-bearing stratigraphy still ahead of us. So, thank you.
Thank you. I'd like to thank William for so smoothly continuing his talk after our break there. And I have a question. I assume some of you might have some questions, so we have a couple minutes. If you have an urgent question, come down to the mic here. And I wanted to ask you about the polygonal cracking that you described at the end. And we've seen that with smectites as well. And I've noticed differences of like 1 meter size and 5 meter size depending on the chemistry of the smectite. And I was wondering what size polygonal cracks you see, and if there are differences depending on the kind of sulfate, and if you see these in the clay sulfate as well, or only in the sulfate. So.
Thanks. It's excellent multiple question.
Yeah.
But it's indeed it's important. The scale is small. It's 4 centimeters, so we're completely surprised by it. We could not see in the distance, and when for them to form in that model, you actually need a bit of clay to help, because you need that contraction, and this is better on a mudstone. So it was at the base of the sulfate-bearing unit where we still suspect clay to be present. So that's why it doesn't mean wet dry cycling only happen here. This is the location where it gets recorded in the form of columnar soil. Mm-hmm. And so here the sulfates and the clay both play a role into forming this lithology. So it's unique. It's the first time we saw it's very small scale you need a rover. Of course, the larger scale, this is a small scale that tells you it's probably high frequency. You dry only 2 centimeter, because the scale of the crack scales by the depth of your process. So if it's a thermal stress of 1 meter, then you make 2 meter cracks. If it's only the seasonal drying of the shallow surface, then it's a small crack. So this has been very consistent forming columns. And so it's been for millions of years possibly.
All right, we have a question. Is that Adrian?
Yes.
Go ahead and say your
Thanks,
name.
Janice. Thanks, William, for the great talk, too. Adrian Brown, Planetarius Research. I just wanted to see if you had an ability to put into your model the findings of the elemental sulfur that has recently come into view.
You're talking about the sulfur that's been found? Indeed, the same instrument we use for sulfates here, we attribute here to sulfates because small amount is diluted in the rock. With the instrument, we can see oxygen, and on the sulfur blocks, it's actually helpful that we can actually differentiate sulfur and sulfates depending on the oxygen signal we see. So on the sulfur blocks, it works. Here in the middle of that mess mixed in the sediment, it's not as obvious to make the difference. So we assume this is sulfates. We've seen it with other instruments as well when we drilled. And so, yeah, that's where we are with that. But happy to discuss more here.
Okay, thank you.
So one more quick question, if that's possible. Otherwise, maybe in the break.
Yeah. Hi, this is Elder from Planetary Science Institute. The thing that kept on coming up for me is that the sulfurites are found in these nodular rocks, like you said. But I hear much more about the nodules themselves. Do you guys have a chance to cut into those nodules, examine them? What are those?
So the nodules are tricky to analyze because we cannot drill them easily. They are centimetric, high relief feature. And so, but we have numerous sampling from the short distance using the laser instruments, CAM-CAM. So from that, we could see their texture also, but we cannot do much more. We cannot drill them as of now. That's something, so yeah.
Thanks.
Let's thank William one more time.
Thank you.